By level 3, you already know Python's basics. Now it's time to see how the language actually works under the hood. In this video we'll cover 4 advanced topics from the Python Mastery Pass Level 3 track: Advanced Object-Oriented Programming, the iterator and generator protocols, decorators and descriptors, and Asyncio-based concurrency. Each one builds on the last, and together they explain a lot of Python code you've probably used without fully understanding. Let's start with object-oriented Python. Beyond basic classes, 5 tools professional codebases lean on constantly: abstract base classes, mixins, method resolution order, cached properties, and meta classes. An abstract base class defines a contract. If payment method declares charge and refund as abstract methods, Python won't even let you create a plain payment method instance, and any subclass that forgets to implement one of them fails immediately with a clear type error instead of crashing mysteriously later in production. A mixin adds one focused piece of behavior through multiple inheritance, without representing a full is-a relationship. Here, product combines a JSON serializing mixin and a name comparing mixin, so it gets to_JSON and sorting behavior for free, with 0 code duplicated inside product itself. When a class inherits from more than one parent, Python needs a deterministic search order for methods. That's the MRO, computed with C3 linearization. Watch what happens when D inherits from both B and C, which both inherit from A. Each super call moves to the next class in that order, not straight to the parent. Functools has a cached_property decorator for expensive derived values that don't change. The first access to report total actually runs the computation and prints that it's computing every access after that, just returns the stored value, with no recomputation at all. A class is itself an instance of something normally type. A metaclass lets you customize how classes get built in the first place, not just how instances behave. Validating meta runs the moment a class is defined, checking that it declares a required underscore field. Bad never even gets fully created, because the check fails before the class object exists. Abstract classes, mixins, MRO, cached properties, and metaclasses all shape how objects behave, but there's a whole protocol underneath the humble for loop, and that's next. Every time you write a for loop, Python is running a specific protocol behind the scenes. Let's build one by hand, then see how generators do the same job automatically. A for loop relies on 2 dunder methods working together: iter, which returns an iterator, and next, which returns the next value or raises stop iteration when it's exhausted. Countup resets its current value inside iter, which is exactly why the same object can be looped over more than once and still work correctly. A generator function writes all of that for you. The moment you use yield inside a function, calling it returns an object that already has working iter and next methods. You never write stop iteration by hand, Python raises it automatically once the function returns. Generators can also receive values back through yield, not just produce them. That's what turns them into simple coroutines. Running _average pauses at yield, and every time you call send with a new number, it resumes right there, updates the running total, and pauses again with the new average. Because generators are lazy, you can chain several together into a pipeline, and nothing runs until the very last consumer starts pulling values through the whole chain. Here, upper wraps non_empty, which wraps read_lines, and each stage only processes one line at a time as it's requested. No stage ever builds a full intermediate list in memory. The standard library's Iterators module gives you fast, well-tested versions of common iteration patterns. Count creates an infinite counter, ilist takes just the first few values from it, and group B clusters consecutive equal items together. Notice it only groups items that are already adjacent. That send-based coroutine style is actually the mechanism async def is built on. We'll get there. First, let's look at how decorators and descriptors quietly control function and attribute behavior. Decorators and descriptors are 2 of Python's most used, least understood tools. Let's see what a decorator actually costs you if you're careless, and what's really going on underneath property. A basic decorator wraps a function inside another function logged, prints a message before calling add and returns its result. But without help, the wrapper replaces the original function's identity, add.name comes back as wrapper, and add.doc disappears completely, which breaks debugging and documentation tools. The fix is one line: decorate your wrapper with functools.wraps, passing in the original function. That copies over name, doc, and other metadata, so add still looks and behaves like add everywhere introspection tools look, even though it's technically running through wrapper. To let a decorator take its own arguments, like retry with times equals 3, you need one more layer, a function that accepts those arguments and returns the real decorator. Calling retry times equals 3 first returns decorator, and that function then wraps flaky exactly like a normal decorator would. A descriptor is any object with get, set, or delete methods, placed as a class attribute. It's what powers property, methods, and static method under the hood. Positive number is written once and reused for both price and quantity, so validation logic lives in exactly one place instead of being copy-pasted. Property itself is just a built-in descriptor. When you write at property on area, you're using a class Python already implemented with get and set for you. Under the hood, it's roughly the same as calling property directly with your getter function. Decorators and descriptors control what happens when code runs and when attributes are accessed. Now let's put all of this to work with real concurrency, using async and await. Asyncio lets a single thread juggle many waiting tasks at once. Let's see why that matters, and how to actually get the concurrency benefit instead of accidentally writing async code that still runs one thing at a time. Calling say_after with a delay and a message doesn't run anything yet, it just creates a coroutine object. Await is what actually drives it. It runs the coroutine until it finishes, or until that coroutine hits its own await and pauses. Awaiting two 1-second tasks back to back takes about 2 seconds one after another, no different from calling them synchronously. Switch to Asyncio.gather instead, and all 3 tasks start together. While one is asleep waiting, the event loop runs the others, so 3 1-second tasks finish in about 1 second total. By default, gather cancels everything else and re-raises the first exception it hits, which can be too strict. Pass return_exceptions equals true instead, and gather collects every result, successes, and exceptions alike, in the same order you pass the coroutines in, so one failure among 10 doesn't take down the other 9. Real async code often needs to cap how many things run at once so it doesn't overwhelm a server. Wrapping each fetch in async with semaphore, backed by Asyncio.semaphore of 3, means only 3 of these 10 fetches are ever in flight at the same time. And when something might hang forever, Asyncio.wait_for wraps it with a timeout here. A 5-second operation gets cut off after just 1 second, raising a timeout error you can catch and handle cleanly instead of hanging your whole program. Between advanced OOP, iterators and generators, decorators and descriptors, and Asyncio, you've now seen the machinery behind most of the magic in professional Python code. It's not magic, it's just protocols. All 4 lessons live on the Python Mastery Path, Level 3. Advanced track links to every one are on screen now, in the order we covered them, so you can go work through the code yourself instead of just watching it fly by.